the Mount Wilson telescope to monitoring the activity of other stars, so quite a variety of classes, some of them G stars like the Sun, many of them not, and they plotted out the level of activity of the star using the peculiar fact that a chromospheric line, that there is a chromospheric line whose internal structure depends upon the level of activity of the star. I have never heard an explanation of what the connection is, but it's loud and clear. And they found one thing that caught my eye. The 11-year cycle for the Sun is relatively long compared to most other stars who manage to pull off a cycle with a period of 2, 3, 4, 5 years. You'll remember that the dynamo has a lot of other possibilities besides the ones that we have been seeing here. That's probably of interest only to those who work in dynamo theory. But I mention this because the dynamo plays such a fundamental role. Remember, too, that the magnetic field of the Sun is in a remarkable fibril state where it comes through the surface. Small fibrils, 100 kilometers in diameter, field strengths of 1,500 Gauss, wide spaces between them where there is no detectable magnetic field. And the problem is it's right at the limit of resolution. That's one of the reasons the advanced technology solar telescope is being developed. And one of the things that is rather puzzling. I don't understand why they're in a fibril state. I can give you an argument, and I can also demolish the argument. So it's a very puzzling thing, and that may or may not be important for the things we're interested in here in interplanetary space. Well, the helioseismology can be done by observing the surface of the Sun, and that was commented on earlier. And it can also be done better from space, and helioseismology will be carried out from a solar orbiter, and one is beginning to see the effects of magnetic fields. I won't speculate on what they will find because I have no way of guessing what they might find. The high-resolution observations from Canova and SDO and Sunrise and so forth all figure into deciphering what is actually happening and checking out the subsurface magnetic fields. That's what we really need is information on the subsurface fields, because there's quite a variety of speculation as to what's going on below the surface, given what can be seen at the surface. Well, there's the solar wind, which is really just the story of the corona. There's the slow wind, the fast wind, and the coronal mass ejection. Perhaps the most mysterious is the slow wind, which emanates from the periphery of active regions, and at least in my mind is somewhat less clear in its structure than the fast wind or even the CME. This is a problem in hydrodynamics and magnetohydrodynamics because it's a large-scale bulk motion. There will be thin surfaces where NHD and hydrodynamics do not apply. For instance, shock fronts. If you have a supersonic flow, you insert a very thin shock front and then require continuity of the bulk flow across that. And you do the same thing with the current sheets, and particularly in rapid reconnection situations, and with shock fronts and other things. So the hydrodynamics gets complicated, and you have to do plasma kinetics in these singular